Hello everyone, and welcome. I'm excited to kick off this presentation on measures of central tendency and dispersion. Today, we'll be exploring the basics of Introduction to Statistics. In this session, we'll cover key concepts that help us understand data better, including how to summarize and analyze data sets effectively. Let's get started. When we talk about descriptive statistics, we're referring to a broad term that often gets used interchangeably with measures of central tendency and dispersion, especially in the context of inferential statistics. Essentially, these statistics help us describe or summarize the key qualities of our data set. They give us a snapshot of what the data looks like without making predictions or generalizations beyond what we've observed. Another way to think about these is summary statistics, which are typically univariate, meaning they focus on a single variable at a time. Some of the most common measures include the mean, median, and mode, which tell us about the center of the data. Then there are measures like range, standard deviation, and variance that give us insight into how spread out or dispersed the data points are. We also look at the minimum and maximum values to understand the boundaries of our data set. Throughout this presentation, understanding these descriptive and summary statistics is fundamental because they form the foundation for more complex analysis. They help us quickly grasp the main features of our data, making the next steps in our statistical journey much clearer. These measures tap into the average distribution of a set of scores or values in the data. When we talk about measures of central tendency, we're essentially trying to find a single value that best represents the overall data set. The most common ones are the mean, the median, and the mode. The mean is what most people think of as the average. Add up all the values and divide by the number of values. The median is the middle value when the data is ordered from smallest to largest, which is especially useful if your data has outliers or is skewed. And the mode is the most frequently occurring value in your data set. Understanding these measures helps us get a clear sense of where the center of our data lies, which is fundamental when analyzing or comparing different data sets. So these three measures, mean, median, and mode, are key tools for summarizing data and understanding its overall distribution. So when we talk about the mean of some data, we're referring to the average score or value. For example, it could be the average age of an MPA student or the average weight of professors who like to eat donuts. Essentially, it gives us a sense of the typical or central value in a dataset. Now, there are two important concepts here. First, the inferential mean of a sample, which we denote as x-bar. That's calculated by adding up all the sample values, which is the sum of x, and then dividing by the number of observations, or n. Second, the mean of a population, represented by the Greek letter mu or mu. That's calculated similarly, by summing all the values in the entire population and dividing by the total number of individuals in that population, n. So, in essence, both of these means are about finding an average, but one applies to a sample and the other to the whole population. And that brings us to the question, what do we mean when we talk about the mean? Well, it's about understanding the central tendency, the typical value, within our data, which helps us make sense of the information and compare different groups or data sets more effectively. So, one of the main problems with using the mean or average of some data is that it can be really sensitive to outliers. For example, imagine we're looking at the average weight of political science professors. If there's one professor in the department who weighs 600 pounds, that single outlier could significantly skew the average. This is what we mean when we say the mean is sensitive to outliers. A single extreme value can distort the overall picture. And that can be problematic because it might give us a misleading sense of what's typical or normal within the data set. So, understanding this limitation helps us see why we might need alternative measures that are less affected by those outliers. This is especially important as we move forward into more robust ways of analyzing data. All right, let's take a closer look at this table. Here, we've got a list of professors along with their weights, and then a second column that shows their cumulative weights as we go down the list. For instance, Schmuggles weighs 165, and Bopsy is also 213, with a total of 378 when combined. Notice how the cumulative weight increases as we add each professor. One interesting point here is that some weights are repeated, like Schmuggles and Schnickerson, both 165, which indicates they contribute equally to the total. As we move down, you see how the total weight builds up, culminating with Professor Zinger's at 308, bringing the overall total to 248.3. This table highlights how individual contributions add up to a larger sum, which reflects the overall weight of all these professors combined. It's a simple but effective way to visualize how each individual adds to the total, emphasizing the cumulative impact. Connecting this back to our broader theme, it's about understanding how individual data points, like these weights, combine to give us a fuller picture of the whole. Whether we're analyzing professors or other groups, the key takeaway is how individual contributions accumulate to shape the overall picture. Because the mean average can be sensitive to extreme values, the median is sometimes useful and more accurate. The median is simply the middle value among some scores of a variable. There's no standard formula for its computation, but the idea is straightforward. It's like finding the middle point when you line up all the values from smallest to largest. Just a quick note. When I say median, I'm not talking about the cement in the middle of the road. It's a useful measure, especially when your data has outliers or skewed distributions, because it gives a better sense of the typical value. So, understanding the median helps us get a clearer picture of the data, especially in situations where the mean might be misleading. All right, let's look at how we rank and choose the middle value. When we have an odd number of data points, we simply pick the middle one after arranging all the values from smallest to largest. But what if we have an even number of data points? In that case, we take the two middle values and find their average. For example, in our table here, we've listed weights of different professors. Once we sort all these weights in order, we identify the middle position. Since we have an even number of weights, 12 in total, we take the two middle weights, which are 165 and 165, and then find their average. That average, in this case, is still 165, making it our median. So the median gives us a good sense of the central tendency of our data, especially when the data might be skewed or have outliers. It's a key concept because it helps us understand the typical value in a dataset. In this example, the median weight of these professors is 165, which is quite representative of the middle of our dataset. Remember, when the data is evenly split, the median is the average of those two middle numbers. This method ensures we're accurately capturing the central point of our data distribution. If we know the median, then we can start to understand how data points are distributed by moving up or down from that middle value. This allows us to rank data relative to certain thresholds, giving us a clearer picture of where individual data points stand within the overall dataset. You might be familiar with standardized tests, like the SAT or ACT, where they tell you your score is in the 90th percentile. That means your score was higher than 90% of the people who took the test, which is a powerful way to contextualize your performance. This introduces the concept of percentiles, which are a way to understand data distribution in practical terms. Instead of just knowing the average, percentiles help us see how individual data points compare to the rest, giving us a more nuanced understanding of the dataset as a whole. So, by using the median and percentiles together, we can better interpret data, compare individuals or groups, and make more informed decisions based on where they stand relative to the entire sample. Now, let's talk about the most frequent response or value for a variable, which we often call the mode. Essentially, the mode is the value that appears most often in our data set. It helps us identify what's most common or typical. However, sometimes we encounter situations where there isn't just one clear winner. Multiple modes can exist, leading us into what we call bimodal or even multimodal distributions. That means we have two or more values that tie for the most frequent spot. And just for a little fun, I like to think of the mode as holding the pie and the Allah, though honestly, I'm still wondering what Allah tastes like. But in all seriousness, recognizing the mode is key because it highlights the most typical or popular response, which can be very insightful for understanding our data better. So, whether it's one mode or several, identifying these most frequent responses helps us grasp the overall picture, especially when trying to understand patterns or common trends. So let's talk about the mode. The mode is simply the value that appears most frequently in a data set. In this case, we're looking at the weights of different professors. When we examine the list, we see that Schmuggles and Schnickerson both have a weight of 165, which is the highest frequency. That means, in this particular data set, the mode is 165. Understanding the mode is important because it helps us identify the most common or typical value in the data. It can also give us insights into the distribution, especially when there's little variability or when certain values tend to repeat more often than others. In this example, recognizing that 165 is the mode can help us diagnose issues like lack of variability, where most values cluster around a certain point. This can be important for further analysis or research, especially if we're trying to see patterns or outliers. So, to sum up, the mode is a key concept because it highlights the most frequent value, giving us a quick snapshot of the most common data point in our set. Measures of dispersion really help us understand the variability in our data. They are also univariate, meaning they focus on one variable at a time. The basic question here is, how much do the values differ for a variable from the minimum to the maximum, and what's the distance among the scores in between? To answer that, we use several key tools. First, there's the range, which is simply the difference between the highest and lowest values. Then we have the standard deviation, which tells us, on average, how far each score is from the mean. Next is the variance, which is just the square of the standard deviation, useful for certain calculations and comparisons. And I want to emphasize that measures of dispersion, like these, aren't something you just cast or ignore. They're essential for understanding the spread or variability within your data. So, as we move forward, keep in mind how these measures help us grasp not just the central tendency, but also how spread out our data really is, giving us a fuller picture of what's happening. To glean information from data, that is, to make an inference, we need to see variability in our variables. Measures of dispersion are really helpful here because they give us information about how much our variables differ from the mean. And this is important because if there's not enough variability, it becomes really difficult to draw meaningful conclusions or insights from the data. Dispersion, also known as the spread or the range of variability, essentially tells us how spread out our data points are around the average. Understanding this spread is crucial for making accurate inferences and understanding the overall picture the data is showing us. So let's talk about the range, which is represented by this simple formula. R equals H minus L now. Here, H stands for the high value, and L represents the low value within your data set. In other words, the range gives us the span, or the difference between the minimum and maximum values of a variable. It tells us how spread out our data is, whether the values are tightly clustered or more spread apart. Understanding this statistic is really important because it provides a quick snapshot of the variability in your data. This is especially useful when you're trying to get a sense of the overall distribution, or when you're making management decisions or trying to diagnose issues. And just to clarify, think of it as the no buffalo roaming rule. If there's no big difference between the high and low, then there's no roaming buffalo, meaning less variability. But if there's a big difference, then your data has a lot of variation. So, in summary, the range helps us understand the scope of our data, and that understanding is key to making informed decisions and interpreting our data accurately within the bigger picture of our analysis. Let's take a closer look at the bell-shaped distribution, or curve. As the name suggests, it has a distinctive shape that's perfectly symmetrical about the mean. This symmetry means that the values on one side mirror those on the other. A key point to remember is that, in this distribution, the mean, median, and mode are all the same. This is a unique property of the normal distribution and helps us identify it easily. Now, you'll notice the tails of the curve extend outward, but never quite touch the horizontal axis. These are called asymptotes, meaning the tails get closer and closer to the axis, but never actually reach it. This indicates that extremely high or low values are possible, but they are increasingly rare as you move further away from the center. This shape, the normal curve, is fundamental because many natural phenomena and data tend to follow this pattern. Recognizing it helps us understand data distributions and apply statistical methods more effectively. So, what does Andre actually do to the sample distribution? Well, he takes a sample from the population and then looks at how that sample behaves compared to the entire population. Essentially, he's examining the distribution of his sample to see what it tells us about the whole group. Now, thinking about the probability of finding someone like Andre in the population, this is where inferential statistics come into play. We want to understand how likely it is that a person with Andre's characteristics would appear in the general population, based on our sample data. And are you ready for more inferential statistics? Because this is just the beginning. We're about to dive deeper into how we can use sample data to make educated guesses and draw meaningful conclusions about larger groups. Remember, the key idea here is understanding how sample distributions help us infer what's happening in the broader population, and how probable certain individuals or traits are within that population. Dr. Boehmer would be here, sharing some really valuable insights, and Andre would also be here to contribute. But for now, let's focus on the concepts of normal curves and probability. These are fundamental ideas that help us understand how data behaves in many real-world situations. When we talk about normal curves, we're referring to the bell-shaped distribution that appears frequently in nature and social sciences. It's important because it allows us to make predictions about data and understand variability. Probability, on the other hand, gives us a way to quantify the likelihood of different outcomes within these distributions. By understanding the normal curve, we can determine the probability of a value falling within a certain range. This connection between the shape of the distribution and probability is at the heart of statistical reasoning, and it ties directly into the broader theme of making informed decisions based on data. So, grasping these concepts is key to effectively interpreting data and applying statistical methods in real-world scenarios. So, what we're talking about here is a standardized measure of distance from the mean. Essentially, it helps us understand how far individual data points are from the average value in our dataset. In other words, it tells us how extreme or typical our data points are compared to the mean. A key point to remember is that about 68% of our cases fall within one standard deviation from the mean. That means most of our data is clustered fairly close to the average. And if we look at two standard deviations, roughly 97% of the data falls within that range. This concept, the standard deviation, is really important because it gives us a consistent way to measure variability across different datasets. It helps us see not just where most data points are, but how spread out they are overall. When we connect this to the overall theme of data analysis, understanding the standard deviation allows us to judge the extremity of cases and assess the reliability or variability within our data. It's a fundamental tool for making sense of the distribution and variability in any set of data. All right, let's take a closer look at the formula for standard deviation. The formula is S equals the square root of the sum of all the squared differences between each data point and the mean, divided by the sample size minus 1. Here, the S stands for standard deviation, which measures how spread out our data is. The square root symbol indicates we're taking the square root of the entire calculation, which helps us bring the units back to the original scale of the data. The sigma, or the sum symbol, tells us to add up all the values that follow. In this case, we're summing the squared differences between each score and the mean. X represents each individual data point or score in our dataset, and the underscore X, or X with a line over it, is the mean of all those scores, essentially the average. Finally, N is the sample size, or the total number of observations or cases we're analyzing. By understanding this formula, we get a clear method for quantifying the variability within our data, which is essential for interpreting the overall spread and for making informed decisions based on our data analysis. So, here we can see that the standard deviation is 165.2 pounds. This number gives us an idea of how much the weights are spread out around the average. A higher standard deviation indicates more variability. But what's interesting here is that the weight of Zinger might still be influencing this calculation, even indirectly through the mean. Essentially, Zinger's weight could be skewing our overall data, making the spread appear larger or smaller than it truly is for the rest of the dataset. Understanding this helps us see why it's important to look at the data carefully and consider potential outliers or influential points that can impact our statistical measures. It also ties into our overall goal of understanding the data distribution more accurately, so we can make better decisions based on these insights. Alright, so the answer we're looking at here is 10.20872 and minus 3.22692. These are the key values that mark the range we're examining. Now, the question is, what percentage of all the cases fall within these boundaries? Based on the data, roughly 68% of the cases are within this range. This is a really important point because it reflects the concept of standard deviation in a normal distribution. Speaking of standard deviations, let's consider the concept of a one standard deviation above and below the mean for democracy. If we take the mean as our center point, then adding one standard deviation to it gives us the upper boundary, and subtracting one standard deviation gives us the lower boundary. This helps us understand how much variation there is around the average. This practice of looking at standard deviations is crucial because it helps us see how data points are spread out, and it ties directly into the overall theme of understanding variability and distribution in our data. It's a fundamental concept that allows us to interpret and compare different data sets more effectively. All right, let's take a look at these values. The answer here is approximately 83.86509 for the first point and 48.36811 for the second. Now, what does that tell us? When we ask what percentage of all the cases fall within these two values, we're essentially looking at how much of our data is contained between these limits. Based on the data, roughly 68% of the cases fall within this range, which is quite typical in a normal distribution, about one standard deviation from the mean. Now, moving on to the next part, what is the value of the urban population one standard deviation above and below the mean? This is critical because understanding the spread or variability in our data helps us grasp how much the urban population fluctuates around the average. This segment is a practical application of standard deviation, which, as you know, measures the dispersion of data points. By calculating that one standard deviation above and below the mean, we can identify the typical range where most of our urban population data points lie. So, in essence, these figures give us a clearer picture of the distribution of our data and help us understand the variability within our urban population figures. Today, we're going to talk about organizing and graphing data. When we collect data, the first step is to organize it in a way that makes sense and is easy to analyze. This often involves creating tables or charts to keep everything clear. Once our data is well organized, we can move on to graphing it. Graphs like bar graphs, line graphs, or pie charts help us see patterns or trends at a glance. They make complex information more understandable and visually appealing. Remember, the goal is to communicate your data effectively, so choosing the right type of graph is crucial. Connecting this to our overall theme, organizing and graphing data are essential skills for making data meaningful and useful in many real-world situations. Now, let's move on to the presentation of descriptive statistics. As we've seen, presenting data visually can really help clarify complex information. Some people find it easier to grasp subject matter when they see visual aids like charts and graphs. This is where scatter plots come into play. They help us provide a sense of the underlying data-generating process. In other words, they give us a visual representation of how the data points relate to each other, revealing patterns or relationships that might not be obvious from raw numbers alone. The main goal of graphing in this context is to make the data more accessible and understandable. By visualizing the data, we can better interpret trends, outliers, or clusters. So, in summary, using scatter plots and other visual tools helps us communicate the essence of the data more effectively, supporting our broader goal of making complex information clearer and more insightful. This slide gives us a picture of the variability and central tendency in our data. Essentially, it helps us understand how data points are spread out and where they tend to cluster around. It can also show us the amount of skewness and kurtosis, which are important aspects of a distribution. Skewness tells us if the data leans more to one side or the other, while kurtosis gives us a sense of how peaked or flat the distribution is compared to a normal distribution. So when we ask, what is the distribution? We're really trying to get a complete picture of the shape and behavior of our data set. Understanding these elements helps us make better inferences and decisions based on the data. Overall, this slide emphasizes that analyzing the distribution is key to grasping the full story behind the numbers. Let's take a closer look at graphing data. Types. When we're working with data, choosing the right type of graph is essential to effectively communicate our message. Different types of graphs serve different purposes, so understanding their key features helps us present data clearly. For example, bar graphs are great for comparing categories, while line graphs are ideal for showing trends over time. Pie charts, on the other hand, help illustrate proportions within a whole. As we connect these graph types to our overall theme, remember that selecting the appropriate graph not only makes your data more understandable, but also more impactful. So, mastering these types empowers us to tell better stories with our data. Alright, so when we create frequencies, what we're really doing is sorting our data either by value or by category. Once we've organized it, we then add up all the cases that fall into each of those categories or values. This process helps us see how often certain scores or categories occur within our dataset. In essence, it answers a pretty basic but important descriptive data question. How often do certain scores happen? By creating these frequency distributions, we get a clearer picture of the data's overall pattern. This is a fundamental step in understanding and summarizing data before diving into more complex analyses. It ties into our overall theme of making sense of data in a straightforward, intuitive way. Alright, so here we have the ranking of donut-eating professors from the most to the least. At the top, we see zingers with a total of 308. That suggests they're really avid donut fans. Next up is honky-dory with 251, which is also quite high. Then we have calzone at 227 and bopsy with 213. You can see the numbers are decreasing as we go down the list. But what's interesting is how these counts give us a glimpse into the donut enthusiasm across different individuals. For example, Google's Boop and Palito, with 199 and 189 respectively, show a slightly lower but still significant interest. Homer, Schnickerson, and Smuggle are close, with 187, 165, and 165, indicating they're fairly consistent in their donut consumption. Boehmer and Levin follow with 151 and 148, and then Queenie at 132. This ranking not only highlights individual preferences, but also ties back to our overall theme of how different personalities or habits can influence our workplace or academic environment. It's a fun way to humanize these figures and see a different side of their personalities through their donut choices. So, it's not just about the numbers. It's about the stories behind them and what they tell us about each person's unique habits. Here we have placed the professors into weight classes and depict with a histogram in columns. What this means is that we've categorized these professors based on certain weight ranges, and then visualized those categories using columns. Each column represents a specific weight class, and the height of the column shows how many professors fall into that category. This setup helps us quickly see the distribution and identify where most of the professors are concentrated. By visualizing the data this way, it makes it easier to compare groups at a glance. It also connects to our overall theme of understanding the diversity within our faculty. Recognizing these patterns can inform future decisions or highlight areas for further analysis. So, this histogram isn't just about numbers. It's about telling us a story of the professor's weight classes in a clear, visual format. Here it is, another histogram depicted as a bar graph. As you can see, this visual representation helps us understand the distribution of our data more clearly. The height of each bar indicates the frequency or count of data points within a specific range or category. This makes it easier to spot patterns, trends, or outliers that might not be obvious from raw numbers alone. Notice how the bars vary in height. Some are taller, showing higher frequencies, while others are shorter. This variation can tell us a lot about the underlying data and how it's spread across different segments. Using histograms like this is a fundamental part of data analysis because it helps us interpret complex information quickly. And as we've discussed earlier, understanding the distribution is key to making informed decisions based on data. So, keep an eye on these visual cues. They often reveal insights that are critical to our overall analysis. Now, let's take a closer look at these pie charts. As you can see, they provide a clear visual breakdown of the data we've been discussing. The first chart highlights the distribution of key factors influencing our results, while the second one shows how these factors compare across different segments. The most important point here is to recognize the proportions, where the largest slices indicate the most significant contributors. This visual approach helps us quickly grasp complex data and see the relative importance of each component. Connecting this to our overall theme, understanding these proportions allows us to focus our efforts on the areas that will make the biggest impact. It's a powerful way to turn numbers into actionable insights. See, if you want to explore other options, make sure to check out the Excel sheet. There's a variety of choices there that can give you different perspectives. Actually, why not consider using a donut graph? Duh! It's a great way to visualize parts of a whole, and it can be more engaging than a simple pie chart. So, don't hesitate to experiment with different types of graphs to find what best communicates your data. Remember, the goal is to make your information clear and compelling. Let's take a closer look at these line graphs, which are a classic example of a time series. As you can see, each line represents how a specific variable changes over time. These visualizations are incredibly useful for identifying trends, patterns, or even seasonal fluctuations within data. What's especially important to note is that time series data helps us understand the progression and behavior of variables across different periods. This can be crucial for making forecasts or informed decisions. In the context of our overall presentation, these line graphs highlight how tracking data over time can reveal insights that static data simply can't provide. They remind us that understanding the temporal aspect of data is essential for accurate analysis and effective decision-making. So here we have a scatter plot, which is a great way to visualize the relationship between two variables. As you can see, each point on the plot represents a data pair, giving us a clear picture of how these two variables might be connected. What's really important to notice is the pattern or trend that emerges. For example, if the points tend to rise together, it suggests a positive correlation. If they move in opposite directions, that indicates a negative correlation. Sometimes, the points might be scattered randomly, showing no clear relationship. Understanding these relationships helps us make better decisions, whether in business, research, or any data-driven field. It ties into the overall theme of our presentation, which is about using visual tools to uncover insights and tell compelling stories with data. So, always look for these patterns when you're analyzing two variables. They can reveal so much about the underlying dynamics at play.